Now we will discuss in section 1.3.1 the surface integral, and the surface integral we also call is a flux integral. Uh, this we write is a surface integral with symbol S, and then the vector function is v dot dA. And if this is a differential area and this is a physical quantity or a vector or a function, and if we are having a closed surface, this is for both open and closed surface. If we are having specifically a closed surface, then we write here a closed means a circle here, and then v dot dA, and this represent the dot product between the vector and the area element. So it is also called a flux integral, that this area is always cross sectional to the vector quantity or to the function. This is surface dependent, and when it is surface independent, then it is a special class that we will discuss later. So for any xy coordinate system, for example, we are having a coordinate system, the x, y, and z here, x, y, and z. And for any surface, let's say this is any piece of a surface, then we are having a length element. This is the length element, which is dA length element. This is a very small or differential area element in a certain direction, and we would like to have the quantity as a dot product through this one. This we call a surface integral. We will understand the things when we will solve an example on this one, and this is example 1.7. Example 1.7, let me recite this example. It says, calculate the surface integral of v, which is 2xz and x plus 2 and y into z square minus 3 and z over 5 sides excluding the bottom of the cubical box, which is side 2 in figure 1.23. Let upward and outward be the positive directions as indicated by the arrows. So let me first draw the figure, and then we will discuss this uh, surface integral. So let's first draw the figure, and this is something like this, that we are having a cube here. So the sides are to be equal, and then here let me write here, and then up to here. So this is our cube, and now our axes are like this, that we are having this is the x-axis, this one is the y-axis, and this one is the z-axis. Now it's a unit, it's not a unit cube, it's two side, means 2 points here. So from here to here means x is 2 here. Similarly, y is 2 here, and z is also 2 here. We are having this face is the face 1 here, which is indicated here. This face is phase 1. Then this face which is inward, means this face which is inward into the board, is phase 2. And then 3 is along Y here, and 4 will be along the opposite Y, it is 4. And then 5 is along the Z axis, while we will have to ignore the bottom side. So here first let me write the vector function, and the vector function is equal to 2xz and x unit vector plus x plus 2 and y unit vector, and y z square minus 3, y z square minus 3 and z unit vector. And we will have to now calculate the surface integral on all these spaces, is excluding the bottom. So the first one, when I calculate this side of the cube, then I know that on this side x is equal to 2. And what about the area element? The area element dA is equal, on this x side, x is equal to 2, so the plane is of y and z, and it will be dy and dz, dy and dz, and it is in the x direction because it is this plane. It is this plane, and the plane is along y and along z, so it is this plane of the cube. Now let's calculate v dot dA here. So this is equal, only this will be multiplied with this, the x unit vector. So it is 2xz and then dy dz here. And we know about x, that x is equal to 2. So it is 4 times z and dy dz here. And now I find the integral. So the integral v dot dA, and this is equal to, let me highlight this one so this is evident, v dot dA, and this is equal to 4 times z, and then 4 let me write here, and let me write here as a separate, that z and dz, while integral dy. Now how much y is changing along this face and how much z is changing? So let's see here. When I want to come to this face, then I will, here at x equal to 2 is this face. Now this face is built how? When y is running from 0 to 2 and z is running from 0 to 2 here, like 0 to 2 here. So these both are running from 0 to 2 and 0 to 2 here. So let's do calculate this one, and I will get 4, then z square over 2 from 0 to 2, and this will be y from 0 to 2, and this is equal, 2 will simplify with this, so it is 2z square, so 2 here, and then 4 square minus 0, so it is 4 minus, this will be multiplied with this, and 2 minus 0, so it is equal to 2 here, and we get as a result 16. 2 into 4 into 2. Now for the phase 2, let me do calculate here. For the phase 2, let me highlight this one as well. Now for the phase 2, which is this one, the phase which is going in the opposite direction to x, and for that one is it is on the origin, so we have x equal to 0 here, and the direction of it is in minus d minus x direction. So the area element dA will be again dy and dz and minus x direction. So it will be minus x direction, means it is minus dx dy and dz here, because this face is outward here, so it is in the minus x direction, and dy dz is minus. So multiplying again with this one, we will get v dot dA is equal to 2xz multiplied by 2xz multiplied by minus dy and dz here, and this is equal, put the value of x and x is equal to 0, so this v dot dA comes out to be 0, and we, when we will find its integral as well, like integral v dot dA, then it will also be equal to 0. Similarly, I can calculate phase 3 here, and phase 3 is the one which is along the y-axis. So when it is along the y-axis, then y is equal to 2 here. For this phase, y is equal to 2, and the plane is being made by the variation in x and z. So the area element dA is equal to dx and dz here, and it is in the direction of y. So what about v dot dA here? V dot dA. Now the y component will be multiplied here. So it will be equal to x plus 2, x plus 2 and dx dz. So do the integral as well. So this is equal to integral of v dot dA for the phase 3, and this is integral, let me split the two, like x plus 2 and then dx here, from x is running, means dx is running from 0 to 2, this is 0 to 2, so this is from 0 to 2, and then dz from 0 to 2 here, means both x y z are running from 0 to 2 here. Now this will come is the integral x square by 2, x square by 2 plus 2x, and then the limits from 0 to 2 multiplied by z here, and the limit from 0 to 2. Now this one will come is, let me do calculate it directly. This will become the limit 4 by 2, so it will come 2 plus 2 into 2, 4. So 2 plus 4 will come out to be 6 here, and 0 of course will give 0, and here it will come 2, so 6 into 2 will come out to be 12 here. Similarly, let me do calculate the phase 4 here. So the phase 4 is here. Now what about phase 4? Phase 4 is the same y, but it is in the minus y direction. So it means that y is 0 here because it's on the origin. Y is 0 here, and dA will be the same but with a minus sign. It will be minus dx and dz here, while the V dot dA product will be x plus 2 and dx dz here, but with a minus sign here, and rest of it is the same, only minus will come in front. So it means that v dot dA will come out for this phase as 12 but with a minus sign. So this is minus 12. And similarly we do calculate the phase 5 as well. So the phase 5, it is equal to, come to phase 5. Now the phase 5 is along the z direction, so it means it is dx and dy plane here along the z axis. So z is equal to 2 on that plane, and the area element dA is equal to dx and dy here, while the vector product v dot dA will come out to be dA. So it is in the z direction, so only the z component will be here. So it is y times z square minus 3. It will come out to be y times z square minus 3, and dot dA will come out is dx dy dx and dy. And we know here that the value of z is equal to 2. So 4 minus 3 is 1. So we are having the y dx and dy here. So we will further calculate this one, the integral, and integral v dot dA is equal to integral dx from 0 to 2, and then y dy from 0 to 2. And this comes out to be 2 here for x, and this is y square over 2 from 0 to 2, and this will come out, the 2 will cancel, and this will come out to be 4. So this is equal to 4. And now I will have to calculate on all the surface. So on all the surface it will be like this. On all the surface will be the one surface plus the second surface, the third surface, the fourth, and the fifth, and they are equal. The first surface gives us 16 plus the second surface gives us 12, while the second surface gives us 0, so we are having 0. Then the third surface gives 12, the fourth surface gives minus 12, and the fifth surface gives 4 plus 4, and the net result comes out to be the 12 cancel and 16 plus 4, so the net result is equal to 20. Means the surface integral or the flux of this vector along these faces, along these area elements, is equal to 20. So this is the way with which we can calculate the flux integral, and now we will start with the volume integral.